So we're going to build upon our concepts of this object, which I call the wave, which I call psi. It's the letter psi, and I remark that this is a kind of field, and it represents the electron, the proton, the photon, the neutron, any particle that we're dealing with in quantum mechanics. Neither has a rigid particle existence, nor does it have a rigid wave existence. Everything is fluid. सब माया है, कभी वो पार्टिकल के तौर पर नजर आता है, कभी वेव के तौर पर नजर आता है. So it's intrinsically objects are neither particles nor waves, rather they are both. So the concept is captured in an object that we denote by psi. Sometimes we call it a field. Not many authors would like to call it a field. Generally this is called a wave function. So the wave function for an object, say an electron, is a very strange object. Now it's strange because since the 1920s, when this object was proposed, people had difficulty understanding what is the significance of the wave function. In normal waves, for example, you have a water wave, right? Now these waves are produced on water, and you can define a certain height for these waves, which we call y. Now this is the height of the water wave. If you have sound traveling through air, you have regions of rarefaction and compression. So you have regions where the pressure is high, and then the pressure is lowered, rarer region, and then you obtain a high pressure region again, the pressure is lowered, and so on. So this is sound propagating inside a medium. These are regions of high pressure, regions of low pressure, high pressure, low pressure. So I can represent this sound wave also in the following form. I have x here, and I have pressure here. Let's call it P. So you have a high pressure region followed by a low pressure region represented by a negative value, high pressure region, low pressure region, and so on. Alright, so you can have, there is something that is waving, there is something that is oscillating, something that is undulating. Alright, this is our normal concept of a wave. But what is really waving inside the wave function? For an electron that is traveling through vacuum or is traversing the double-slit apparatus, what is it that is really waving? It's vacuum, there is no medium. So this was a question that a student asked yesterday, and I would like to highlight the importance of this question, and I would like to answer this question today. So what is it that is really waving? Or in other words, what does psi represent physically? Now the point is that psi on its own does not represent anything. It is devoid of any physical significance on its own. Just psi does not have a direct physical meaning. But what is meant by a physical meaning? Physical meaning का मतलब ये है कि what do we observe in an experiment? So the outcome is not directly dependent on psi. It depends upon psi mod squared. This object has physical meaning. Psi on its own does not have a direct physical meaning. It's just the amplitude of the matter wave associated with the electron. It's just the amplitude of the field, but it does not have a direct physical meaning. For example, if you have light propagating in vacuum, what is light? It's an electromagnetic wave. So what is waving in light? आप बताएं, जो पीछे तीन बैठे हुए हैं, आप में से कोई बताए कि what is waving in an electromagnetic wave? जी, इलेक्ट्रॉन. ये क्या बात हुई? इलेक्ट्रोमैग्नेटिक वेव में इलेक्ट्रॉन्स होंगे? आप बताओ. फोटॉन्स होंगे, लेकिन what is waving? What is the amplitude representing in an electromagnetic wave? The propagation of the photon. So this means if I draw an electromagnetic wave like this, does this mean that the photon, there's a photon that is going up, and then it comes down? Is this what the electromagnetic wave means? आप बताएं, थर्ड नंबर पे आप बैठी हैं, आप बताएं कि what is waving inside an electromagnetic wave? What, this axis is time or distance. What is the vertical axis? This is a very simple question. आप बताएं, आप गिरों में से, कि what is the vertical axis in an electromagnetic wave? Anyone?
Electromagnetic field.
It's an electric field. This axis is an electric field. So there is an electric field that is waving. So whenever electromagnetic radiation passes through a medium or through vacuum, it's really an electromagnetic field that is going up, down in amplitude. So the strength of this field is going up, down, and so on. There could also be a magnetic field associated. There is a magnetic field associated with it, which is perpendicular to the electric field. So this is in the horizontal plane, while the electric field is in the vertical plane. So whenever we have a wave, we have something that is undulating, something that is oscillating. G.
Electric field always is vertical plane.
No, it can be in any direction. Depends upon the polarization. Alright, so you have an electric field that is oscillating. That makes up an electromagnetic wave. So does this electric field have a physical significance? Yes. The electric field makes physical sense. It is physically plausible. You can measure the electric field somehow and you have proper units for it. You have volts per meter as units for the electric field. But this function, this field, is unlike any other wave, because you cannot really tell what the vertical axis represents. Okay? So if I were to draw a wave function, suppose this is x, and I'm drawing the wave function at time t equals 0. So I'm drawing the wave function. So if my wave function looks like this, at time equal to 0, this wave function is a function of x as well as time. But I'm putting time t equals to 0. So I've drawn a wave function. Now this is the field of an electron, the pilot wave of an electron, or a photon, or a neutron, or any particle, quantum particle that we are studying. It is the field of that particle. Now this field is present in space, and we don't really know what is the meaning of this function per se. At least we do not know it on the equal footing as we know of for an electromagnetic wave, or for a sound wave, or for a water wave. However, if we take the modulus squared of this function. Instead of psi, if I were to plot psi mod squared, can you tell me what this function will look like? All the negative values will turn into positive values, right? So I will get something like this. Now this function, which is the modulus squared of psi, does have a physical meaning. Okay? And what is the physical meaning? The physical meaning is that this function psi mod squared represents probability density. And what does this mean? This means that now this is a function of x and we are considering time to be equal to 0. What this means is that psi, which is a function of x, modulus squared times dx is the probability of collapsing the field between x and x plus dx. अब आपने आज का लेक्चर बहुत तवज्जो से सुनना है. It's semi-physical, it's semi-philosophical, because quantum mechanics has a little bit of philosophy in it as well. तो बड़ी तवज्जो से सुनना है. खाली टेक्स्ट बुक से समझना मुश्किल होता है. अब पहले आप इस स्टेटमेंट को जरा पढ़ें, इसको जरा देखें आपको समझ आती है कि नहीं, and then I'll explain what it means. Now suppose we have an electron that is moving in space and the electron's wave function is given by this yellow wave. Okay, this is the electron's psi, the electron's wave function. The probability density associated with this yellow function is drawn here. Now this electron is moving in space. This point is x equals 0. This is some x naught. This is some 2x naught, some 3x naught, and these points are in between. Now the electron is in space and we're not observing it. We don't care about the electron. The wave function is there. Nothing happens to the electron. It's there and you're not observing it. So you're not disturbing the electron. Okay? So this is a pristine system. You're not disturbing it. You're not looking at the electron. You're not shining photons on it. You're not observing. You're not an observer. You're not measuring. The electron is in its own world and it's happy and you're happy. But if you want to measure the electron, where the electron, if you want to answer the question, where is the electron, you would have to observe the electron. Okay? You would have to measure the electron. Alright? Now comes in an observer. Now if you look at this wave function and the modulus squared of this wave function, it goes from minus infinity to plus infinity. So this wave function fills up all of space. It's everywhere in space. Okay, because this wave function is going from minus infinity to plus infinity. Alright? So it's everywhere in space. Okay? So what this means is that this wave function psi fills space. It's everywhere. So even though there is a single electron and you're not observing it, it's everywhere. ठीक है, हर जगह है, हर जगह मौजूद है ये इलेक्ट्रॉन. लेकिन अभी आपने उसको देखने की ज़हमत गवारा नहीं की. Before you observe the electron, it's everywhere because its field is filling up all of space. इसको कहते हैं हर जाई, हर जगह पैदा है, हर जगह है ये इलेक्ट्रॉन, हर जाई है, हर जगह है. लेकिन अभी आपने उसको ऑब्जर्व नहीं किया. ठीक है, क्योंकि वेव फंक्शन और उसका मॉडुलस स्क्वायर्ड यही बता रहा है कि द इलेक्ट्रॉन has a wave function that fills up all of space. So there's a field of the electron that's everywhere. Now you want to measure it. You want to detect where the electron is. You ask me the question, ये तो बताएं कि electron है कहाँ? So I would come up with a microscope or some other arrangement or some other kind of detector, and I would like to see where the electron really is. Alright? So suppose I place my detector at this point here. This is where I can place my detector. I don't have a detector or a camera that can look at all of the space. I can only look at one pixel or one narrow region in space at a time with a detector. ठीक है? Quantum mechanics is only good because you can justify your experimental results with it. If you can't do any measurement, quantum mechanics is useless. ठीक है? वो तो फिर एक ब्लैक बॉक्स है, ना आप कभी उसको देख पाएंगे ना वो आपको कभी देख पाएगा. वो तो एक ब्लैक होल हो गया. तो quantum mechanics is useful because you want to do a measurement, you want to observe something. So you have to be an experimenter who observes where the electron is. Otherwise आप नेचर के बारे में कोई मालूमात हासिल ही नहीं कर पाएंगे. नेचर को देखना, उसको महसूस करना, ये एक मेजरमेंट है, ये एक ऑब्जर्वेशन है. So you have to make an observation. So you place a detector at a particular point in space. Now there is a probability that the electron will be observed at this point. Okay? And that probability is given by the height of this function at this point. If you place your detector here, where the modulus squared of the wave function is 0, no matter how long you wait, the electron will never register its presence on the detector, because the value of the modulus squared is 0 here. If you place your detector at this value of x, there will be the highest probability of detecting the electron. So this function, which is the modulus squared of psi, is actually proportional to a probability. And if you place your detector in this region, so that the range of the detector is this. So the detector does not see one point in x, it sees a range in x. That's what every detector will do. It sees a range in x. Okay? Suppose this point is x dash, this point is x dash plus dx. and the range of the detector is dx. Let me see if you can see from the back. नजर आ रहा है पीछे से? ओके अब देखो आपके पास एक डिटेक्टर है जिसकी लेंथ dx है, जिसका फील्ड ऑफ व्यू dx है. एक कैमरा लें, अगर आप तस्वीर खींचें तो हो सकता है आपको दीवार का कुछ हिस्सा नजर आए. अगर आप जूम आउट कर दें दीवार का बड़ा हिस्सा नजर आ सकता है. सो यू कैन हैव अ डिटेक्टर दैट हैज अ सर्टेन फील्ड ऑफ व्यू. ओके, सो दिस डिटेक्टर measures anything between x dash and x dash plus dx. In other words, the width of the detector is dx. So there is a finite probability that the electron will appear in this range, that the electron will be registered on the detector, and that probability is given by this area. This area divided by the total area under psi square. Now what is this area? This area, if dx is very small, so let me redraw this figure little bit zoomed in so that I can explain things a bit more clearly. So now my detector is between x dash and x dash plus dx. This is my detector, and I place my detector here and I wait for it to detect the electron. There is only one electron. Okay, now what is the probability that this detector will click with an electron? कि उसके ऊपर इलेक्ट्रॉन आएगा और वो क्लिक करेगा या वो रजिस्टर करेगा कि इलेक्ट्रॉन इस रेंज में प्रेजेंट है. उसकी प्रोबेबिलिटी निकालने के लिए you take this region of the curve and find the area under this curve. And I want to shrink dx so that the probability of finding the electron in this region, that is the area of this yellow shaded region, will be psi x mod squared dx. So this is the probability of finding the electron in this narrow region. And if this region is wide, for example, if I would like to detect the electron between x dash and x double dash, if my detector is this big, then the probability of finding the electron in this range will be given by this area. And I can find this area by writing the integral of psi x mod squared dx from x dash to x double dash. एक मिनट, ठीक है? चलिए पहले सवाल पूछता हूँ, आप लोग थोड़े से गुम हो गए हैं. चलिए सवाल पूछते जी. It is infinitesimally small, but this is how you will compute the probabilities for any wave. There is no particle that has this wave function. It's only an idealized particle.
The probability is zero.
The probability is very small in this case. G.
So why is that the wave function itself has no physical representation, but squaring it gives us a physical representation?
All right. So now this question has been asked for about 90 years or so now. Why doesn't psi have a physical significance on its own? Psi is a mathematical construct. We wrote the wave equation for normal waves, and that was d square y over dx squared is given by 1 over velocity squared d square y over dt square. Do you remember this equation? The wave equation? So y represents some amplitude of a wave. Now this amplitude of the wave satisfies this equation. Similarly, psi will satisfy some equation which is called the Schrodinger equation. So the wave equation for psi is called the Schrodinger equation. So we use the Schrodinger equation to calculate psi, and then when we calculate psi, at the very end we calculate psi modulus squared, which has physical meaning. But that does not mean that psi is unimportant. Psi is being used for calculating psi mod squared, but directly only psi mod square has a physical meaning. Okay, more questions? Alright, so if you look at this expression, is this term is some probability. Okay, this term is some probability. So what are the dimensions of dx? Length, right? So what should be the dimensions of this object? 1 over the length. 1 over length. So if this is probability, this is length, what is this object? This is probability per unit length. Okay? This has to be the proportional to the probability per unit length, and that is why it is called the probability density. Okay? It's probability per unit length. This is the length. This gives the probability. So this is probability per unit length, also called the probability density. Alright? Now let's build up this concept a little bit further. Now these are very subtle concepts. There's no mathematics involved, but these are deep concepts. So they should really sink into you, because the rest of the course is building upon these concepts. Now suppose I have a free electron. I've drawn it as a particle, and it's moving in space. Okay? Now if I would, this is the particle picture. It's moving with a velocity, say v. The energy of this particle, suppose it's moving at very low speeds. So we take the non-relativistic energy, which is just half mv squared. Now this particle is moving with a certain velocity, it carries a certain energy. Now associated with this particle is a field or a wave function. And I mentioned that that wave function can look like this. It's zero everywhere, and it's non-zero only in a certain regime. So if this particle moves forward, if this particle comes here, the wave function also moves forward. Psi, or this is psi. Psi also moves forward. The particle moves even forward, even to the right. The wave function moves to the right with it. So the particle is moving, the wave function is moving along with the particle. Now if this is psi, I can also draw psi mod squared. Psi mod squared will just be the square of this. So I can draw, this is psi mod squared. This is the wave function at one particular point in time. At another point in time, at this point in time, the wave function looks like, the modulus squared of the wave function looks like this. At yet another time, the modulus squared of the wave function looks like this. And so on. So I can plot the wave function and I can plot the probability density. So if I have my detector, this is the x-axis. If I have my detector placed here, this is my detector. Initially, I will not observe any electron when this is the wave function, the modulus squared of the wave function. As this modulus squared of the wave function passes through this detector, there is a high probability that my detector will click. Okay? So what's going to happen then? Now do you understand this point, that when this modulus squared of the wave function intersects the region of the detector, there is a high probability that the detector will click? Okay? And what happens when the detector clicks? So that's another question we would like to answer. Suppose, once again, let's look at this example. This is x at some time, and what I am plotting is modulus squared of x, psi x, and this is my wave function. This is the probability density, sorry. If I place my detector here, this detector is never going to click, even though the electron's field is everywhere. The electron has a field that fills up all of space. But if I place my detector at these nodal points, the detector will never click, because the modulus squared of the wave function is 0 here. At any other location, if I place my detector here, here, any other location away from the nodes, my detector will click. Now what is the meaning of a click? What does a click mean? You register an electron. An electron falls on the detector. जिस तरह हमने कल वीडियो देखी थी जिसमें an electron strikes a CCD camera, it produces a white spot. Alright? Okay. So a white spot is produced or a click is produced. ठीक है? It can produce a visual spot or it can produce a beep. Detector आके गिरा, इलेक्ट्रॉन गिरा डिटेक्टर पे, एक बीप प्रोड्यूस हुई, क्लिक की आवाज आई, अगला इलेक्ट्रॉन आया, क्लिक की आवाज आई. So energy is produced. Okay? So where is that energy coming from? That energy is coming from the electron,
which had the kinetic energy initially.
Right, which initially has the kinetic energy. So the act of measuring means that you are picking up energy from the electron. Okay? Now before you made a measurement, the wave function or the probability density is everywhere. So where is the energy of the electron? It's everywhere. The electron is everywhere. एक ऐसा भूत है इलेक्ट्रॉन जो हर जगह, इट्स एवरीवेयर. उसकी एनर्जी स्पेस में फिल अप हुई है, उसकी एनर्जी हर जगह है. लेकिन when you are registering a click, all of the energy of the electron gathers up bunches together and transfers itself to the detector. So the act of measurement gathers all energy from the space filling field. और इसको कहते हैं कि psi has collapsed. Just concentrate on this sentence. Psi this is psi mod squared x x. The top two curves, these two curves represent the state of the electron before measurement. Okay? Before measurement. Now what happens after measurement? Suppose you place your detector here. Now there is some probability that this detector will click. Suppose it doesn't click. You wait for a long period of time and it doesn't click, which means you haven't observed the electron. It means you haven't disturbed the electron, which means that the wave function remains intact. Okay, you have done nothing to the wave function. The wave function remains where it is, but you know nothing about the electron. Okay, the wave function remains intact. Now this probability is not 1. This detector will not click with certainty. It will only click with certainty if this modulus squared is 1. But it's not 1. So there is some finite, non-zero, but non-certain probability that it will click. If it doesn't click, you're not disturbing the electron. The wave function remains where it is. But that's no good because you know nothing about the electron. You haven't measured the electron. The electron is going its own way. You haven't interfered in its life. Okay? However, if the detector clicks, because there is a finite probability that it will click, then this wave function collapses. Why does the wave function collapse? Because now all of the energy that previously filled up all of space has now gathered together, bunched up, and hit the detector and produced a click or a beep or a visual sensation or something, because energy has to go to the detector. Now that energy is coming from the electron. The electron was previously everywhere, but all of the energy has now garnered together, become a capital, and registered itself on the detector. This is what we call a particle. This is what we generally call a particle. So a particle is a bunched up capsule of energy taken from the space filling field. And once this detector has clicked, you can draw a new wave function. The original wave function collapses and a new wave function is produced. That new wave function is given by something like this. The wave function, the new wave function, the original wave function has collapsed into a new wave function. So the original wave function has lost its meaning. Now you have a new wave function. This wave function can over time evolve into the older wave functions, but at the act of measurement, the wave function collapses. You see, if you don't perform a measurement, quantum mechanics is mathematically beautiful. Everything works seamlessly together, but it's useless if you don't do a measurement, because you're not observing nature. In order to gain something useful about nature, you have to observe it. But the very act of observing collapses the wave function. It mars the beauty of quantum mechanics. But you have to stick to observing, because without observation you cannot make any sense of what nature is doing. So the other question is, if this is the wave function, how would we know that this is the wave function? Because we are placing our detector only at a particular point. We don't know anything about what's going on at the other points. So how do we get this wave function? This one. With a single electron, we cannot get this wave function. Right? As you observed yesterday, in order to observe single electron interference, you had to pass one electrons through the system, one electron at a time, but a large number of electrons, in order to get the interference fringes. You can't tell anything with a single electron. With a single electron, you can only talk about this probability. But how do we get this probability curve? In order to get this probability curve, you have to perform repeated measurements. You have to have many identical electrons, and you need to place your detector, you need to sweep your detector at different locations. You have to sweep the detector. In order to construct this probability pattern. So even though with one electron, if you knew that this is the wave function, this is the probability density, you can tell what the probability is. But if you wanted to construct the wave function, you would have to perform measurements with multiple identical copies of electrons, and the detector has to be swept. Or you need to have a detector which has a large enough field of view, which can detect all space at one time, and that is only an omnipotent being. जो हर जगह प्रेजेंट है, जिसे हम लोग खुदा कहते हैं. अच्छा, last thing, it's very important to have a recourse to yesterday's lecture. And how do we define or describe the double slit interference pattern in light of what we've learned today? Just 3-4 minutes. ये देखें, this is the scheme of the double slit interference pattern with electrons. This could be one electron at a time, multiple electrons, it doesn't matter. What we observe is that if the wavelength of these electrons is of the same order of these slit widths, you observe an interference pattern. And we mentioned that if you have a single electron, you cannot tell that that a pattern is observed. The pattern builds up over multiple electrons, but a single electron can never fall on this place, it can never fall on this place, it can never fall on this place, never on this place. With maximum probability it will fall here, it will fall here, it will fall here. Okay, so what is going on in terms of wave functions here? What is going on is that a single electron comes, it has a wave function psi. Now that single electron splits its wave function into two parts, even though the particle is not splitting. The particle electron can never split. ठीक है, it's a fundamental particle. इलेक्ट्रॉन को स्प्लिट नहीं किया जा सकता, और हमने ये ऑब्जर्व भी किया था कि अगर हम इसको ऑब्जर्व करें तो इलेक्ट्रॉन either comes here or here. So the electron never splits, but the wave function splits. ठीक है, और इसका मतलब क्या है? इसका मतलब यह है कि एक wave function for the electron passing through S1 is psi1, and the wave function for the electron passing through S2 is psi2, and then these wave functions interfere, and at this point you will get the sum of these wave functions. You will get psi1 plus psi2. ठीक है, अब ये wave functions स्प्लिट हो गए, लेकिन स्प्लिट एक अच्छा लफ्ज नहीं है क्योंकि इलेक्ट्रॉन इज नॉट स्प्लिटिंग. सो व्हाट वी से इज दैट इन दिस रीजन हियर द इलेक्ट्रॉन has a wave function that is the sum of psi1 and psi2, and the electron's wave function is psi1 plus psi2. And this is called a superposition. So the electron is in both the state psi1 and psi2 at the same time. The combined wave function of the electron is psi1 plus psi2. The detector, this detector will click with a certain probability. And what is that probability going to be? It's going to be psi1 plus psi2 again modulus squared. The probability that this detector will click, if this distance is say some z, the probability that this detector will click is psi1 at z plus psi2 at z modulus squared. So now we have a wave function that fills the space, and the electron is present in a superposition. On Tuesday I'll tell you about the Schrodinger cat as well, but the electron is now in both of these states at the same time. Okay, and when this detector clicks, the wave function collapses, it disappears. Okay, so now interference fringes are observed because this object is different from this object. These two objects are not at all equal. And this is something I'm going to build up on Tuesday, inshallah. Thank you very much.